it's Mr. Otwell, the Math Master, helping you master math, and today we're going to be talking about log properties. This video is a little longer than normal, but it is going to be very good to just lay that solid foundation of logarithms that we're really going to need in order to be successful when we're dealing with log expressions and log equations. We're gonna hit on what is a logarithm as well as those main properties that we're really gonna be using. If you find this video helpful, please make sure to subscribe, hit that notification bell, give me a like, give me some feedback. Let me know, did you like the video? Was there something that you think I could have explained a little differently? Or anything would be great. Let's do this. So for some of you, this might be your first experience with logarithms, and welcome. They're so much fun. I really love them. They're very useful. They help us to deal with exponents, and we'll start to see this here pretty soon. So I just want to start with really the basics. What is a logarithm? It's something that kind of looks like this, okay? If we see this equation right here, it's read, like when you see it, you speak it as log base b of a equals x. And I wrote it right here, right? What is this really asking us? You have to understand that a logarithm is an operation. It's like addition and subtraction and multiplication. All these operations you've been familiar with for a really long time. It is also an operation. If you have some expression, log base b of a, it's telling you something. It's telling you to think about something. It's saying, b, okay, this little number here, this most of the time it's a number, to what power gives us a? That's what it's asking. So I just went ahead and added this x here. This whole thing is saying b to what power, normally in math, if we don't know what something is, we just call it x, is equal to a. This is what a logarithm is actually telling us to do in terms of an operation. There's two main forms. We have logarithmic form here and exponential form here. Because if you noticed kind of what I was saying, we're saying b to what power is a. That's what a logarithm is telling you to evaluate. So you could really rewrite that as a completely different equation that we have notation to do. B to what power, call it x, we don't know, equals a. This is logarithmic form. This is exponential form. Being comfortable with flip-flopping the forms when needed is really the key to logarithms, in my opinion. There's other ways to go about it, but if you can just drill this in your head, okay, log base b of a equals x is the same as b to the x power equals a. What I want to draw your attention to so that you can start to connect these ideas, it's really going to help you remember the fact that log base b of a equals x is the same as b to the x equals a, is check what I've been saying. What do we call this little number right there? What do we call this guy? We call this the base. This is the base of the logarithm. What do we call this number here? This is something we're a little more familiar with, more than likely, having some exponent here. We actually call this big number down below this little guy up here, we call that the base. And do you see how the base of our logarithm is the same as the base of our exponent? Okay, really, if you think about it, there's three things you're needing to identify in all of this. Dude, if you know just that the base is the base, right? There's one out of three. So even if you're just guessing from here, which you don't have to because you'll have a really good feel for all of this here in a minute, you already have 2 out of 3. You got a 50-50 shot at getting it right. Another thing that I like to mention is that if we look over here, x is what? What do we call that? We call it the exponent, right? So b is our base, x is our exponent. So there you go. There's 2 out of 3 parts. Log base b of a equals x is the same as b to the x equals a. You really need to memorize this. Like right on your pillow, just sleep on it, let it just absorb into your brain. I don't think it really works like that, but you could try. Why not? Just tell me how it goes. So let's just deal with kind of a standard logarithm question you might see. If you had log of 100 and they said evaluate that, Right now, you might be asking yourself, okay, Mr. Otwell, well, you didn't write anything right there. Over here, there's these little things right here, these little numbers, but you didn't write anything. Yes, you're right. But another property you need to keep in mind is that as mathematicians, we're lazy. We don't write stuff if we don't have to. I'm here to tell you that number right there that we write right here is 10. If you ever see a logarithm with no base written, the base is a 10. We just don't write it. It's kind of like if you just had x, no number in front, no exponent up here. There is really a coefficient here, and there really is an exponent. We just don't write it because we're lazy. We know that the coefficient is 1. Like, this is really 1 times x. We just don't write 1. And we also know that the exponent is a 1 because x to the 1 power is just x. So, if you add 1 times x to the 1 power, you just get x. We don't need to write all of this stuff. We just understand that it's there when we need it. Same idea goes here. We don't write a base sometimes when we're dealing with logarithms. If there is no base, the base is 10. But it still begs the question, what is log base 10 of 100? Now remember, this is asking you to evaluate something. It's saying 10 to what power is going to give you 100? 10 times itself, how many times gets you 100? Well, we know that 10 squared is equal to 100. 10 to the second power is 100. So log base 10 of 100 is equal to 2 because 10 to the second power is equal to 100. So this is just a really quick example of what it would look like to evaluate a logarithm. It gets much more interesting than this, and I'm going to touch on those types of examples later on in another video. So be on the lookout for that one. It's going to be good. So now let's take a look at the most common logarithm properties that we use. At first, this looks really intimidating. There's all these letters, there's all these numbers, there's like a word in the equation now. You're used to variables, but now we have the word log. Maybe you've seen sine and cosine, tangent, so it's not as bad. But these are not as bad as they look once you kind of get the pattern and see the connections of how they work together. So if we just read this is log base b of x times y, because remember, if we write variables right beside each other, there's multiplication going on right there. So log base b of xy equals log base b of x plus log base b of y. Now notice what happened here. Okay, we had a product inside. We have two factors. X is a factor and y is a factor. And then we split those up. The base remained the same. Okay, whatever that base is, b, it stayed the same. And the factors get split into two separate logarithms. So what if we had an example? What would that look like? What if we had log of 2x? Well, what's the base? We just don't write it. Is it 10, right? Yeah, you're catching on. What's going to happen here? This one logarithm is going to turn into what? 2. So we're going to have two separate logs. But what are they split by? What is separating them? A plus sign. The reason there's a plus sign really goes back to exponent properties, and maybe in another video, if you're interested, I can prove where these properties come from. I think it's really cool. We'll just stick with examples for now. The one logarithm becomes 2, so it's going to split into 2 logarithms. Remember, the base stays the same. We just said the base is going to be a 10 here, but we don't have to write it. If we don't write a base, we know it's 10. If the base is 10, we don't ever write it. So we would just stick with this. Now, what's going to happen here? Remember, this is 2 times x. This is 2 factors inside the logarithm. We're going to split. One factor is going to go in one logarithm. The other factor is going to go in the other logarithm. So where's this 2 going to go? Right there. And where's this x going to go? Right here. So notice our factors got split into 2 separate logarithms. This is what we call the product property of logarithms. If we move down here, we have log base b of x over y. So now inside the logarithm, we have a fraction, and it's equal to log base b of x minus log base b of y. Notice, these two look really similar, and I want you to see this. These are very, very similar. So really, if you memorize one, you're going to know the other. Let's just get an example under our belt of how this works, and then I'll try to tie those together for you. For example, we could have log base 2 of 5 over 8. Now, if we take a look over here again, what happens? the argument, that's what's in the logarithm, we call it the argument, it's a fraction. And notice the numerator gets split into one logarithm and the denominator gets split into the other logarithm. Take a look what's in between. We have a minus. So this one logarithm will become two logarithms. So don't forget though, our base b does not change. If this was log base 2, this will remain log base 2. And remember, we're going to have subtraction in between because here we have a fraction. Where does that numerator go? Right there, right in that first logarithm. So our numerator is a 5. So in the first logarithm, we're going to have a 5. What's our denominator? It's an 8. So what's going to go in that second logarithm? That 8. So we know that log base 2 of 5 over 8 is the same as log base 2 of 5 minus log base 2 of 8. This is what we call the quotient property of logarithms. Now let's talk about how these are really similar, and basically if we can remember one, we'll be able to remember the other. Look inside this logarithm. We have multiplication, right? And in between the logarithms, we have addition. If we go down to this property, what do we have in the logarithm? We have division. And what do we have in between the logarithms? Subtraction. Notice, what's the opposite of multiplication? Division, right? What's the opposite of addition? Subtraction. So if you can remember, one is just the opposite of the other in terms of like inverse operations. Boom, you're good to go. You know one, you'll know the other. This operation, multiplication, x times y, usually makes numbers bigger. And look, this operation here, addition. Addition usually makes numbers bigger. So the operations that are paired together that make stuff bigger, they stick together. They're buddies, right? Division usually makes things smaller. Subtraction usually makes things smaller. So the operations that make stuff smaller, they're buddied together too. If you remember one, you can remember the other. You got this. You can do it. So let's take a look at our third property we're going to be using quite often. We have log base b of x to the n power is equal to n times log base b of x. So what does that look like with numbers? What if we had log base 4 of y to the second power? Well, that's going to be equal to, check it, does our base change here? No. So this will be a log base 4 still. And this logarithm, inside the logarithm, the exponent was an n. But where does the n end up? On the other side of the equation. It's right in front. It's a factor. So this 2 is going to end up in front of our logarithm and multiply it. What happens to our base? Nothing. It just stays there. So our base is a y, and we'll keep this as y. This is what we call the power property of logarithms. Log base b of x to the n power is the same as n times log base b of x. And last but certainly not least, we have the change of base formula. Notice what happens here. Log base b of a becomes something where we actually change the base. In all these other properties, we are not messing with the base. We have to keep those bases the same. But this property allows us to actually switch the bases whenever we need to. This might seem a little intimidating with all the letters and variables and stuff, but just notice this a, this goes in the numerator, and the b here goes in the denominator. C can be whatever we want. Most of the time when we're changing a base, we want it to be like base 10 or for a natural log base e, and we'll get there here in a minute. So if we had log base 3 of 8, that would be equal to, look what happens here. We have a log, and then it splits into two logs, where one logarithm is on the top in the numerator, and one logarithm is on the bottom in the denominator. So we just split that one logarithm into two new logarithms, and basically in this case, I'm just going to let c be 10. Because like I said, most of the time we're even using this property, we're changing it to base 10 or base e. Once again, we'll get there in a minute. So just as a side note, c is 10 in this case. I chose c to be 10. In the change of base formula, you get to change the base to whatever you want. So notice the number that's literally above, like the b, right? We have base b of a. The number that's literally above the other is gonna stay above the other one. This 8 is going to stay above the 3. So log base 3 of 8 is equal to log of 8 divided by log of 3. I could have changed the base to whatever I want. It could have been log base 2 of 8 over log base 2 of 3. So these are our main properties that we use when we're dealing with logarithms. The product property, the quotient property, the power property, and our change of base formula. So let's just scroll on down here a little bit. We've got another property that we need to discover. Actually, two. Let's do two, shall we? Actually, three. Let's do three. I would like to pose a question for you. What if we had 10 to the power of log of x? So 10 is our base here, and log of x is the exponent itself. Sometimes when I'm evaluating a logarithm or an exponent, I would flip back and forth between an exponential form and logarithmic form so that I can just kind of think about it a little bit better. It might kind of shed some light on what I'm even looking for. So let's do that. If we can take our expression, what we're given, and identify b, x, and a, we can take those values, substitute them into logarithmic form, and we're good to go, right? Well, in this case, what is b? Well, b, remember, is our base, and our base is 10. So I just can write that down. Our b is 10. For our case, what we're looking at, b is equal to 10. Now, what's our x? Our x is our exponent. Our exponent is log of x. It's all the entire logarithm, the whole thing. So the exponent here is log of x. Now, we're missing a here, but really, you can just add it if you want, because the question here is 10 to the power of log of x is equal to what? Well, let's just call it a. We have an a here for our exponential form, so we might as well just kind of keep it consistent. So what is this value? Well, in our case, a is a, okay, so a is a. Now we can take a, b, and x and substitute them into logarithmic form, and maybe this would kind of shine some light on what 10 to the power of log of x is. So we start with log base b, our b is 10. So this expression is equal to log base 10 of, we're going to put a inside the logarithm here, and our a is just a. So we put a here, and it's equal to what? Well, it's equal to x. What's our x in this case? Well, we're saying x is log of x. Now, one thing that's good to note here is this is log base 10. We don't have a base here, so what is it? We just don't have to write it. It's a 10. So putting the 10 here really helps us consider what are we dealing with. Because remember, we are trying to determine 10 to the power of log of x is equal to what? Well, look at our equation. Okay, we have log base 10 of a is equal to log base 10 of x. Log base 10 of a is equal to log base 10 of x. So notice our log base is equal on both sides. And remember before, I mentioned logarithms are operations. They're doing something in the expression or equation. This is kind of the same as saying 2 times 3 is equal to 2 times what? Well, what do you know about what this x has to be? Well, if you're multiplying the left side of the equation by 2 and you're multiplying the right side of the equation by 2, those operations, those mathematical operations are the same. If this is a 3 here, what does this have to be? For this equation to be true, this x must be a 3. 2 times 3 is 6, and this would have to be 2 times 3 to get you 6. The same idea is going on here. Because we have log base 10 of some argument equals log base 10, same base of some other argument, what do we know about a and x? They must be equal. A has to be equal to x. So if we take our answer, x, for a, and we substitute it in right here, this is what we would get. 10 to the power of log base 10 of x. I'm just going to throw that little 10 right there, right? It's there, we just don't write it. Log base 10 of x is equal to what? Well, we found that a is just x. You see what happened there? If the base of our exponent is raised to some power, that's a logarithm that shares the exact same base, then whatever's in the logarithm in the exponent, that's the solution, like every single time. So we've discovered a new property. Oh, there it is. B to the power of log base b of x is equal to x. If our exponent's base and our exponent's base of the logarithm are equal, those are inverse operations. They undo one another, leaving us with just x. Now to find our next property, let's move myself up. Whoa, there I go. Hey. What if we had something kind of similar? What if we had log base 3 of 3 to the x power. What would that be? Well, we don't know what it is yet, so let's just call it y. So in the same way we determined what this exponential form would be in logarithmic form, we can change this from logarithmic form, right, to exponential form. All we need to do is identify b, a, and x, and then substitute those values into this form. So what's our b? Our b is 3, right? 3 down here. What's our a? A is what's inside the logarithm. Our a is all this right here, 3 to the x. So a is equal to 3 to the x, because it's all this. If we wanted to stick with the same colors here, we could just make this red right there, right? And what is our x? Well, our x is y. So x is y. Now we just take all the variables we just found and plug them into exponential form. B in this case is 3. So that's 3 will be the base of our exponent. What's our x? Well, our x is equal to y. So we're going to write a y up there, and that's going to be equal to a. What's our a? A is 3 to the x power. So 3 to the x power. Now look at what we have here. What if I change the colors up on you again? Remember how before this 3 was yellow? Oh, you see it? 3 is the base here. 3 is the base here. Same idea as what we talked about before. This is like 3 as our base. It's being exponentiated by y. Big math word, but it's okay. 3 is our base here being exponentiated by x. So if our bases are equal, what do we know our exponents have to be? They have to be the same. So what we found is that y is just equal to x. So if we plug that back in right here, if we substitute that back into our original expression, we would get log base 3 of 3 to the x power is equal to what? What's our y equal to? It's equal to x. So look at that. We found another property. You see that base of the log is 3, and then the base of what's in the log is also 3. What ended up happening? You see how you could consider these just canceling each other out? These are inverse operations. They undo one another. So we found another property. Log base b of b to the x is equal to x. If the base of your logarithm is equal to the base of what's in the logarithm, those cancel out and just leave you with the exponent itself. There's one more really important property of logarithms that we want to make sure to take note of. So let's just scroll down a little bit here. Here we go. If we consider something like log of -2, what would that be? What would that be? Log of 2 is equal to x. If we wanted to evaluate the log of -2, what would that get us? As I mentioned before, sometimes when you're evaluating a logarithm, it makes a little more sense in your head to just switch it into exponential form. So let's just switch it into exponential form and see what we get. So remember, exponential form is this up here, b to the x equals a. So log base b of a equals x is the same as b to the x equals a. So I just went ahead and wrote it down here so it's easier to reference. What's our b here? Our b is 10. So b is equal to 10. B is the base is the little guy right after the log. What's our a? A is what's in the logarithm. What we have in the logarithm is -2. A is -2. And then what's our x? Well, we just called it x. So x is x. So when we substitute it into exponential form, our base was 10. So we put that as the base. Our exponent was just x. So we write x as our exponent. And our a was -2. So this will help us think about it. 10 to what power is equal to -2? That's what we're asking ourselves. If we're evaluating log of -2, we're saying 10 to what power is equal to -2? So let's just think about this a minute. 10 to what power is -2? Well, you know, if x was positive, if we put a positive number in right here, 10 just gets really big, right? That's really not going to give us a negative number. So x can't be positive. That's not going to work. Oh, what about negative? If x is negative, what happens? Well, remember, negative exponents don't turn numbers into negative numbers. They make the reciprocal. They flip them. Any negative exponent here is not going to give us a negative answer. Just as a quick example, if we had 10 to the -2 power, that would be 1 over 10 squared. Remember, the negative exponent just flips it and turns it positive. So that just gives us a fraction, right? We're not getting a negative number here if we put a negative exponent. Oh, what about 0? We could check 0, right? Oh, yeah. So, well, 10 to the power of 0, well, we remember that from our exponent properties as well. Anything to the power of 0 is 1. It can't be negative, it can't be 0, and it can't be positive. So what the heck is x going to be? Nothing. It does not exist. It doesn't exist. There is no number we can raise 10 to and get a negative number. It's impossible. So what are we learning here? We are finding that you cannot have a negative inside of a logarithm. You can't take the logarithm of a negative number. It just does not exist. This is not an operation we can do. For example, we can't divide by 0. It's undefined. Taking the logarithm of a negative number is undefined. It does not exist. So what we've just found is you can't take the logarithm of a negative number or 0. The same logic applies. If you had the log of 0, 10, there's nothing you can raise 10 to get 0. Remember, we're either going to use positive numbers, get a really big number. If we use negative numbers, it gets us a fraction. So we could get really close to 0, but we could never get 0 because if you use 0, you get 1. So you can't take the logarithm of a negative number or 0. It is undefined. That leaves us at our last little note here. There's one logarithm that is oh so special. It's the natural log, and it will look like this. We would just say like the natural log of x. Now, you might be saying, well, why is this so special, and why did you write ln rather than log? Well, there's something here. We just don't write it, ever. If you ever see ln, natural log, there's always the exact same base and it never ever changes. If you see the natural log of x, the base is always e. Now what is e? E is Euler's number. It is a number. It's kind of like pi. It's an irrational number, goes on forever. Natural logs are so important. Basically, if we're ever using logs in the real world, the natural log is what we use. E is just this amazing number that always pops up in the world. It really is pretty amazing and beautiful. So what we need to know is that the natural log is a special logarithm. So what that means is that all of these amazing properties up here, these logarithm properties, they all apply to the natural log as well, because the natural log is just a special logarithm. So if you ever see any of these situations happening where just instead of logarithm or log base b of xy, you had like natural log of xy, the exact same property holds true. Natural log of xy would just be natural log of x plus natural log of y. So really, we can call these natural log / logarithm properties because they're kind of the same thing. Just remember, the letters might be different. You might see log or natural log, but the rules are all the same. So that wraps it up with our logarithm properties. If you found this video helpful, please subscribe, hit that notifications button, make sure you're seeing all the videos coming out. Please leave a like, leave a comment. Tell me what you thought. Mr. Otwell out. Peace. X power. Whoa, whoa. Oh no. Share with me your thoughts. I will see you guys. Did you like the, B, X, and A thing?